All right, so your next homework assignment is related to evaporation. That's what we're going to be talking about today and Tuesday in class. Assignment's due on Thursday. And so this topic of evaporation comes from section 3 in chapter 7 of your book. And it's the sort of thing where we're just going to learn some of the fundamental principles in evaporation. I'll show you an empirical method for estimating evaporation. But the people who do this for a living, who do like evaporation estimation, I've never seen anything as difficult as when I tried to apply evaporation to a watershed here in West Virginia. It's the hardest, it's the hardest thing I've ever done. It's really, it's in-depth and sophisticated, so it's tough stuff. We're just going to barely be scratching the surface. So before we get into it, what factors do you think would influence evaporation rate? And so it may be, when I say evaporation, I may be saying from a free surface of water, like a river or a lake or a pond. But evaporation can also encompass the loss of water from plants. So what do you think would promote evaporation? Just think about the factors that are out there in the world that would increase versus decrease evaporation. Okay, humidity. So make a statement on what kind of humidity would increase evaporation. All right, so low humidity will increase evaporation rate. What's your rationale for that? Good, yeah. So one of the principles we've already talked about when we were discussing precipitation is the fact that there's a limit for solubility of water in air. The air can only hold a certain amount of water before it's fully saturated. And there's a principle in chemistry, and actually lots of different fields, that the further away you are from saturation, the faster the rate is. And as you approach saturation, then the rate of exchange decreases. And so we'll see some of that today as we talk about evaporation. So the statement, low humidity will increase evaporation rate. What other factors is going to affect evaporation? Temperature. All right. So let's put it in terms of the same kind of statement. So you were going to say?
Higher temperature, more likely you're going to have evaporation.
Higher temperature will increase, all right, evaporation. All right, now I'm going to ask a follow-up question. Temperature of what?
Air.
Okay. Higher temperature of air. And what's your rationale there? Why would warmer air increase the evaporation rate more than cooler air? This is kind of a two-step thing, like an if-then. If the air is warmer, then it has a higher capacity to hold moisture. Remember that the solubility of water in air is temperature dependent. And so the whole reason there's precipitation is as that air rises, it cools, and cooler air can't hold as much water. And so here we're saying higher temperature air can hold more water, and so therefore it's going to have a lower relative humidity. So warming up air is just basically going to increase the capacity of that air to absorb water. And so evaporation is we've got some liquid, so this is the liquid phase, and it's going into the vapor phase. And so it's the contact of two different things. You've got the contact of a gas and a liquid. And so what we're saying in this first statement, higher temperature of air will increase evaporation rate. Basically, we're saying that the air, by being heated, now is able to accept more moisture than it could have when it was cool. All right? Now, what about the water? How might the temperature of the water be affect evaporation rate? What's another statement that we could say?
The closer it is to the gas phase as far as temperature, then the more quickly that it can evaporate. Because it doesn't have as far to travel temperature-wise. So if it's ice, then you're going to have to heat the ice. You're going to have enthalpy is going to have to be such that it can melt and then evaporate.
Okay. I think part of what you're saying is true, but let's say, what if the air was 20 degrees Celsius? So the way you phrased it was, the closer the water temperature is to the air temperature, the faster the evaporation rate will be. And I think that that's true to a point. You know, ice won't evaporate as quickly as 20 degrees Celsius water, but what if it was 90 degrees Celsius water? It doesn't necessarily have to be close to the air temperature is my point. So yeah, so what we could say is higher water temperature will increase evaporation rate. Okay. Are there other things you can think of that would promote evaporation?
Wind.
Very good. Wind. So why?
More air would be going over the water.
Okay. So
Evaporate.
yeah. Precisely. So how would we write that in a statement in terms of more of this will lead to more of that?
Higher wind will increase evaporation rate.
Okay, higher wind will increase evaporate. Very good. All right. So that lays a good foundation for what we're going to be talking about today. I think we've captured the main factors that lead to evaporation. Evaporation is essentially, there are two components that dictate the rate of evaporation. One is the energy that's available to volatilize a liquid, and the other is transport of liquid vapor away from the surface.
Would vegetation also affect this? Not that it...
Yeah, if we're talking, so the sketch I put on the board here was just like a pool, a free surface of water and air. So if we're talking at the watershed level, you know, if we're thinking about a watershed in West Virginia compared to a watershed in Arizona, you know, vegetation would be one of the factors that's going to affect the different rates of evaporation. And we'll get into how vegetation affects that. Yeah, the short answer is yes, it will. Okay, so let's watch a couple of little video clips here that maybe will help us to visualize evaporation and some of these different effects as they're actually happening. One is a time-lapse video. We're actually going to watch water evaporate. It's like watching paint dry. Yep. Okay, so we watched a puddle evaporate in class today. Is there any class more boring than hydrology? What's next? All right, but I think there's something that we could learn from this. And one of the things is that there's more water in the region that's shaded than in this dry area over here, the sunny region. You notice that the puddle isn't, for the most part, in that sunny spot. And it evaporates more quickly in the part that is exposed to the sun than the part that isn't. And that could potentially just be the initial depths, but I think that the sun also plays a role in it. Okay. Here's another look at evaporation.
Does the sun have like the temperature, like how it influences?
So your question's about the sun? Yeah, we're going to look at some slides that show the different types of radiation. But it all is just, it's delivery of energy. That's the sun's role is delivering energy. There's nothing besides that as far as evaporation is concerned. All right, this is something, the Leidenfrost effect, where if you have an extremely hot surface, the evaporation occurs so quickly that actually the water is cushioned by a thin layer of vapor. So they pour in some water, and the sizzling as the water dances around on that hot skillet is because it's vaporizing so quickly, it's kind of like a hovercraft in a way. The water droplet is on a cushion of air. So we've just seen some evaporation there. So in the first case, the first video we saw was evaporation, and the heat that was driving it was ultimately coming from the sun, because that's what keeps the air in the atmosphere at a certain temperature, and it's the atmospheric conditions that have this concrete at a certain temperature. And if we were to measure the temperature of the pavement, it would probably be warmer in the direct sun than the pavement that's just in contact with air of a certain temperature. And that's why I was in a rush this morning. I didn't put the sunshade up in my car. And I know because I'm facing that way. Let's see, I guess that's west, right? The sun sets in the west. So in the afternoon, when I sit down in my car, the seats are going to be really hot. Hotter than they would be if I was parked in the shade. The air temperature is the same, but I'm receiving solar radiation all day onto my seats. And so we'll talk about the difference between long wave and short wave radiation in just a minute. But what this is showing is that the energy source was the sun. In this, the energy source was a gas, probably natural gas of some sort, that heated this up. And so the evaporation was a lot more rapid because there was an abundance of energy. Okay, here. We'll look at evaporation in Canada, how they do things in the Great White North. I better. Yeah, so this is up in Yellowknife, Northwest Territory. And it's so cold that the temperature gradient between the air and the water means that as soon as the water droplets get up into the air, that it immediately evaporates. It goes into the vapor phase because the air is very dry when it gets that cold. Okay. How an igloo keeps you warm. That sounds interesting, but not today. All right, one last. This is evaporation in a vacuum.
The pump.
We've talked about this in fluid mechanics, how it's possible to boil water by removing the vapor pressure around removing the atmospheric pressure surrounding the liquid. And so those little bubbles, those gas bubbles, that's H2O. And it's going into the vapor phase very easily because the pressure is lower surrounding it. So evaporation, I guess one other factor we could have written would be related to atmospheric pressure. Like evaporation occurs more quickly at high altitudes than they do at lower altitudes. One of the warnings they gave us when I did this race in Colorado over the summer was that you need to hydrate more than you normally would, because we were up at about 13,000 feet, and you just, as you exhale, you lose more moisture than you do under normal lower conditions, partly because of the atmospheric pressure, and the tendency to evaporate at a low pressure is greater for the liquid. All right. So this is a figure from your book that is showing differences in wavelength for incoming solar radiation compared to outgoing long-wave radiation. So the sun is shining in the visible and ultraviolet range. So here the wavelengths are in terms of microns. And then as the energy is absorbed by the Earth, it's emitted back into space, but it's emitted at a different wavelength. It's not in the visible range. It's in the infrared range that energy is emitted once it like if you've walked in front of a brick wall, for example, in the afternoon, you kind of feel that heat radiating off of the wall. That's an example of long wave radiation, as it's called. So short wave radiation and long wave radiation. Here's a figure that breaks it down by amount. And it's, we do mass balance in environmental engineering, and it's also useful to do energy balance and look at where is the energy coming from that actually drives evaporation, and what are the factors that limits evaporation, and one of them being the available sun. So if there are 100 units of radiation that come in contact with the outer atmosphere, then a good portion of that is reflected into space before it even actually gets to the surface. Out of 100 units, and the radiation intensity that actually comes in contact with the outer atmosphere is 1367 watts per square meter. If we could capture all of that and we had a 100% efficient solar panel, then it would be possible to get more than a kilowatt per square meter of solar panel. And that's definitely not what we're actually getting from solar panels at Earth's surface. I think the most efficient solar panels are somewhere in the range of maybe 20 or 30%, and what we're actually getting at the Earth's surface is so much lower than what comes in contact with the atmosphere, because the air itself causes backscattering. Then there are clouds, a fraction of which reflect energy back into space. The atmosphere absorbs some of that, and then the atmosphere is going to emit it. But about half of the incoming solar radiation that hits the outer atmosphere is absorbed by the surface, whether it's the sea or whether it's soil. And how many of you have ever seen the movie An Inconvenient Truth? It came out more than 10 years ago, but it's about global warming and climate change. It's got Al Gore in it. Okay. It's a politically charged movie. A lot of people don't like it because they don't believe in global warming or climate change. But one of the interesting scientific points it makes is that water and land absorb energy at a different rate. And the polar ice caps absorb energy at the lowest rate because they're being white, they tend to reflect the incoming solar radiation. And so this 50% absorbance, here it's saying reflection by surface is only 4 out of 100. Well, that's an average over the entire globe. The polar ice caps are able to reflect a lot of the sun, but as they melt and more of it is turning into ocean, then water absorbs a lot more of the energy than the ice used to. The ice mostly would reflect it, water mostly absorbs it, and so it's kind of there's a feedback loop there that as the sea ice melts, there's more energy absorbed, and that promotes additional melting of the sea ice. All right, so there is some fraction of the incoming radiation that's absorbed, and then it is all emitted back out to the atmosphere. There's maybe over decades just a minuscule amount of heat accumulation. But over the course of a single season, all of that energy that comes in has to go out. Otherwise, there would be a huge increase in temperature inside of the closed system that is our atmosphere and Earth. So there is a small increase in temperature over time, but everyone's saying we want to keep the temperature change below 4 degrees Celsius over the next century. And so that's a relatively small change. What we're talking about, there's a lot of incoming radiation, and the same amount goes out. So I want to be clear, I'm not saying that there's no such thing as climate change. There definitely is, but this mass balance is over the short term rather than over the long term. It's energy balance, rather. All right, so shortwave radiation is solar incoming radiation, and what you need to know is terrestrial long-wave radiation is at those longer wavelengths, and so it's the difference between the two that accounts for the energy that can be used for evaporation. So here's just, again, the typical wavelengths for that energy, a figure that the two amounts are equal. It's just the area under the curve will be the same, but the direction is different. Another one of the factors that affects the rate of evaporation and how it's different at the equators than it is at the pole, besides just the fact that at the poles there's a lot of ice, and so that's going to affect evaporation, that's going to affect how much energy is absorbed, this is showing the projected area that's influenced because of the curvature of the Earth. So at the equator, this incoming solar radiation, if we were to take a unit area of it, then the projected area is about the same as that incoming unit area. But then at the poles, because of the curvature of the Earth, the sun is coming in a collimated way. We're so far away from the sun that the sun's rays are coming in a single direction towards us. If the two were close, let me just do a little sketch here. So if this was the sun and here was the Earth, then the sun would be shining at an angle like that. And so the incoming rays, though, because we're so far away, it's essentially collimated, which means all of the rays that get to us from the sun are coming from a single direction. They're not coming at an angle because of the vast difference in the vast distance between them. So they're all coming in the same. Do you have a question?
Yeah. So is there no refraction from when it leaves the sun, that space in between Earth? Is there no refraction of any kind?
No, because there's no gases in space. There's refraction because of the thin atmosphere. The angle of the incoming radiation is deflected because of the atmosphere, but this one-dimensional radiation, we can think of it's the same as if we had a beam of light. One of the instruments I used when I was working on my PhD was called a collimated beam, and it's where you would have a light source, and it's encased in a box that has a hole and then another box with a hole here and a hole there, so that the light that comes down is all one directional. Even though the light was shining in lots of different directions up here, it's shining in all the different ways. By having a series of concentric rings, then what comes out is just going to be like a spot, and it's collimated. The intensity is the same everywhere inside of the beam. And so it's kind of the same here, where each one of these I sub SCs has the same amount of solar radiation, but the area that it's projected over is much larger at the poles. And so that means that the intensity at the poles is a lot lower. So that's the spatial variation of radiation on the Earth's surface. And another way that the radiation varies is over the course of the season. And so we all know that here in the northern hemisphere that during the summer months, for us the middle of the year, June, July, August, September, we have longer days because the Earth tilts as it rotates around the Earth. As it orbits, there's the period where let's see, the vernal equinox is where it's equally, the northern and the southern hemisphere have an equal amount of radiation because the equator itself is closest to the sun. But then at the winter solstice and the summer solstice, then that's the period that the poles are pointing towards the sun the most, and they're tilted the most towards the sun. And it's kind of interesting. Sometimes you may see globes that have a pattern on it that show. Have you ever seen a globe that had like a calendar and it shows the dates and where the sun is actually pointing towards that part of the globe during a certain date. And it's interesting to see that it's not a linear process. And if you look at the sunset times, right now we're going through a period where the sunset time is changing a lot each day. But then as you approach the winter solstice, then the sunset times get very small. The change each day will maybe just be 1 minute or 2 minutes. But there is a period during the year where the sunset times are changing by like 12 or 13 minutes. So it accelerates and it's nonlinear. Humidity is one of the factors that you identified, and it affects the rate of evaporation. And there is the possibility of water vapor being in the vapor phase even when the temperature is below 100 degrees Celsius. And we know that that's the boiling point for water, but some of the molecules in a body of water will have enough kinetic energy to be in the vapor phase even below that. We need to think about what a normal distribution looks like. And remember, a normal distribution is like a bell curve idea. And what it means is that even when the overall temperature is maybe 20 degrees Celsius for water, some of those molecules, because of like multiple collisions, are going to have enough kinetic energy to escape into the vapor phase from the liquid phase. Although not all of them are going to have enough kinetic energy, a small fraction of them will. And so as you increase the temperature of the water, what it does is it shifts the number of molecules that have sufficient kinetic energy. So there's going to be a greater number of them that have the kinetic energy required to go into the vapor phase as you increase the temperature. And it's the heat and energy from the sun that is keeping that water vapor as a gas. And so the moisture that's in the atmosphere stays in the atmosphere, partly because there's a constant exchange of heat, and so there's a constant exchange between the liquid in the oceans and the liquid in lakes and rivers and the gas phase. So if you want to zoom in on the interface between liquid and gas, there are some molecules above the liquid layer, and the way that we measure that is generally in terms of the partial pressure. If atmospheric pressure is 101,325 pascals, then one of the ways to measure how much moisture is in the air is by the partial pressure that's being exerted by the nitrogen, by the oxygen, and also by the water vapor that is in that mix of gases that's in the atmosphere. Now, the amount of water molecules that we would measure is either by relative humidity or by the partial pressure. And so the liquid water molecules vaporize because as the sun is shining down, that excites the particles, gives them the kinetic energy and the collisions that they have enough movement to break through that membrane at the top, the surface tension membrane, and into the atmosphere. Across the globe, the rate of evaporation from a free surface of water would be higher, but the average across the globe is 3 millimeters per day. So that takes into account both the fact that about 2/3 of the Earth's surface is liquid, 1/3 of the Earth's surface is land, although some of that land has moisture in the soil, some of the evaporation is occurring from plants. But across the Earth, about 3 millimeters per day is the spatial average of evaporation. There's a constant for water, how much energy is required to vaporize a kilogram of water. So this is the number of joules per kilogram, and it is partly temperature dependent, although if you look at 2.5 times 10 to the 6th, it's going to be a relatively small effect of the temperature. The warmer the water is, the less energy that's required to vaporize it. But this is a constant we'll use in the empirical equations we have that allow us to estimate the rate of evaporation, is this latent heat factor. This is a photo that I took while I was driving to work one day. Shouldn't probably be taking pictures as I drive, but I couldn't resist because this is the Ohio River, and there was this persistent cloud formation immediately above the river itself. Everywhere else was a clear day. And maybe you've noticed a similar thing before, that it's foggy near the river. And so why do you suppose that would be? Why would there be a cloud that hangs just over the river? Okay. Yeah, when it's about the same width as the river and right over the river, it kind of makes you think, well, that moisture maybe came from the river. During the fall, when the air is cool, the water is warmer than the air. Water changes temperature more slowly than air does because it has a higher density, and so it holds on to temperature a lot longer. Oceans lose temperature more slowly than the air does. Like if you go to northern Europe, the temperature in northern Europe is a lot warmer than it ought to be based on its latitude because of the ocean currents that take water from the closer to the equator up towards Europe.
I actually live on the river.
Mm-hmm.
During the fall, we go out and if you go on the balcony in my house, we look out, you can see right through the fog.
Mm-hmm.
But, downstairs, you see right below it is just above the river. I'll have to send you the picture. My stepmom takes them all the time.
Yeah, I'd love to see that. I bet that sounds pretty cool. Remember that lifting is the cause of precipitation, because what lifting does is it increases the relative humidity of air. And so what we're seeing here is if the water is warm, then it's heating up the air that's right above the water, and that heated air will rise, and as it rises, its relative humidity goes from relatively high to being completely saturated. And then the moisture has to go into water droplets. Yeah?
So I think for this phenomenon to occur, there's probably no wind.
That's right.
It would
Yeah, it's on a still day. Mm-hmm. Yeah, if it was breezy, then it would just move that out of the way before it had a chance to saturate immediately above the river. All right, so here's another look at the solar radiation, and it's breaking it up into the incoming solar radiation, which is all short wave, and the stuff that is either backscattered or reflected by the clouds or reflected by the surface, that's all short wave because it hasn't been absorbed. But if it is absorbed, then it's emitting long wave radiation. And the difference between the two is how much energy there is that is able to drive the evaporation that we're interested in. If water is reflecting energy, then that's not energy that's available to evaporate. The water has to absorb it for it to drive evaporation. So of course we have to have balance between incoming and outgoing radiation. Otherwise there would be an accumulation and we'd cook just in a matter of hours. But evaporation modeling, there's two main approaches, and one of them looks at energy being the limiting factor. The other looks at transport as the limiting factor, meaning moving the moisture away from the surface as the limiting factor. So in the energy balance method, what we're trying to do is come up with some sort of a way to calculate how much energy there is to provide that latent heat of vaporization. So remember, that was how many joules of energy is needed to volatilize a kilogram of water, to take it from the liquid state into the vapor state. In the energy balance method, what we do is we have a free surface of water and we take a certain unit area of it, And we keep track of the heat that is lost from the water to the ground. So here that's G. And we have to look at how much heat is lost to the air, the sensible heat to the air. The net radiation is going to be the amount of radiation that's already taken into account the reflection off of the outer atmosphere, the absorption by the air before the radiation gets right to the water surface. And what we want to do is keep track of how much this water level is going down. The decrease of H is the evaporation rate. So the change in the depth of water over time, dH dt, so it's negative because it's going to be decreasing as this water evaporates. That is E, the evaporation rate. So our overall goal is to have an equation that predicts E. And you'll notice here that we have a mass balance where this vapor that's flowing out of our control surfaces is the density of the water times the cross-sectional area of this unit area that we're considering, and then the evaporation rate. So even though it's a water level that's decreasing, what we're keeping track of as the outflow in this mass balance is going to be a gas, but it's the mass balance is the same because the amount of mass we lose as a liquid is the same as the amount of mass of air moisture, of liquid moisture that goes outside of the control surface. Okay, so this equation is saying that here in the liquid phase, the mass that's lost through the control surface is equal to the mass that is inside of the control volume. So it's the reduction in volume over time and the flow out through the control surfaces. And that is going to be a velocity that it's exiting and a cross-sectional area. So the two terms, this is a lot like the Reynolds transport theorem that we learned back in fluid mechanics, where we're saying there's a difference between storage and transport, and that difference accounts for the loss of mass over time. So if we assume that we were going to be doing this sort of a calculation on like a metal pan, where we weren't going to lose any water through the pan, like it was just only going to be evaporation that we were keeping track of, we'd say there's no storage term, and so the liquid phase is just about how much the mass is being lost due to a decrease in height. And so what we're saying is that this liquid inside of the control volume is decreasing at the same rate that the vapor is flowing out. So essentially, the mass flow rate is the density of the water, the cross-sectional area of the pan, and the evaporation rate. That's in the liquid phase. Now in the vapor phase, it's that same m dot, the same amount of mass that was here as a liquid is now as a gas, and we're going to assume steady conditions. So the rate of change is equal to 0, and so it's all accounted for by some specific humidity. And specific humidity, this Q sub V, is the ratio of the mass of water relative to the mass of air. And it's only a little bit of moisture that can be absorbed by the air. And so to have, like in the headspace above this liquid, to have that moisture taken out, there has to be some dry air that comes in to replace it. Otherwise, it'll become fully saturated and the evaporation will stop. So in steady state, for us to have some constant evaporation that's driven by solar radiation, what we're assuming here is we're saying that there's unlimited transport, but really what is slowing down the rate of evaporation is just how much energy is able to be delivered. So the sun is shining, it's providing the latent heat of vaporization, and that evaporation rate occurs because of the latent heat of evaporation. The latent heat of vaporization has been satisfied. So we're assuming steady flow by just saying that incoming dry air is in plentiful supply to take the place of the moist air that has to be removed, otherwise evaporation won't continue. So what we do is we keep track of, through the control surface, that the density of the air multiplied by the specific humidity tells us the amount of water that's there, and then the velocity times area is a volumetric flow rate. So that's essentially the amount of water mass that's exiting through the control surface is accounted for by that liquid rate decrease that we were seeing with E. So this is just a complicated way of saying whatever evaporates goes out of the control surface as additional moisture. And if we increase the velocity of that transport, then that can increase the rate of evaporation. If you have a larger cross-sectional area, then that's on an absolute basis is going to increase the amount of evaporation. And if we're keeping track of the evaporation rate, then what we've done is just we've moved the water density and the cross-sectional area that the evaporation is occurring from over to the right-hand side of the equation. And you can define the evaporation rate not only by just measuring this liquid level decrease, but another way to estimate the evaporation rate would be to measure what's going on with the gases. And the reason why this is significant is that it may be that maybe the liquid rate isn't going down. It could be that you have a river coming in to a lake. And so we know that evaporation is happening, but the water level doesn't go down in that lake because of a stream that's feeding it. So what this is saying is another way you could find out what's the evaporation is look at the flow of the gases through a control surface. Look at how does the specific humidity change because of it being in contact with this the liquid. How is the specific humidity over the lake different than the humidity that's over maybe dry land upwind of that lake? The energy balance method requires us to keep track of the amount of heat that's put into the system. And in this equation that we're going to go through, we're going to actually keep track of the net radiation that's available to drive evaporation. So this R sub n is going to be an important part of the equations. Let me just put it all on the screen here so we can look at this element of water. We have the incoming solar radiation, and then there is a certain amount of it that's reflected. And so the net radiation that's going to be driving evaporation is the difference between the radiation that comes in, subtracting out the reflected radiation, and then the emitted radiation, this R sub E, is the long wave. And so what we're saying is consider that tank of water and the energy that goes into it. Energy comes into the tank, energy is reflected from the tank, and energy is emitted. The difference between all of that is the net radiation that's available to drive evaporation. So evaporation is consuming some of the energy. It will be the difference between what goes in and what goes out. So we calculate that net evaporation, and then we subtract out things like how much energy is being lost because the water is going to, if the water is warmer than the ground, you're going to have some energy through ground heat flux. You're also going to have some energy that's lost as the water heats up the air that's surrounding, that's right above the liquid surface. And so the total amount of heat that's available to drive the evaporation, this dHdt, the rate of heat input, takes all those factors into account. There's lots of different things that have to be satisfied before there's any energy left over to drive evaporation. So this evaporation rate, we're saying, is what we need to know is the net radiation flux, the latent heat of vaporization, and then the density of the water. Let's see. We didn't get to go over that quiz, so we still have some time. We're going to continue. Let me delete this announcement slide, and we'll keep talking about the oh, this is a good one. Heroic broken sewage pipe floods Congress. That's from The Onion. You ever seen The Onion before? Okay. All right, so back to evaporation. Let's try using this formula that we've just seen with some concrete numbers here. In the UAE, they've got these lagoons that are kind of like inland water bodies that are just nice little, they're not lakes because they're connected to the ocean, but they do have a lot of evaporation because it's so warm there, and people often measure the salinity because of the excess evaporation in those lagoons. But let's just look at some specific data that I took from the internet. I was able to get data that described the incident radiation in this lagoon at noon on February 12th, so 978 watts per square centimeter, watts per meter squared. And that's a lot lower than about the 1,500 watts per square meter that you get in the upper atmosphere. So there's been some absorption, some reflection, and so on. So that's the incident radiation. That's the R sub I. The water temperature is 26 degrees Celsius. And the reason why that's significant is that, remember, the water temperature influences how much energy is needed to vaporize a kilogram of water, so the latent heat of vaporization. The relative humidity is 75%, and the wind speed is 1.7 meters per second at 2 meters of height. Now, you don't yet use this relative humidity or wind speed when all we're doing is considering the energy. Remember what I said is two different things that are the driving factors in what is causing evaporation. One is how much energy is available. The other is how much transport is available. All we're considering now is just the available energy. Later on, we'll look at a combined method that takes both of those factors into account. But so far in this energy method, we're just assuming that there's an unlimited amount of transport of liquid vapor, and evaporation is just driven only by the available energy. All right, so let's put some things on the whiteboard here. First of all, the reflectivity of water, it's called albedo, A-L-B-E-D-O. So it's the reflectivity. Its alpha is 0.35. Oh, I guess it was already there. We've got that alpha is 0.35. Emissivity is 0.995. The Stefan-Boltzmann constant we're going to need to plug in when we are calculating this amount of radiation that's emitted by the water. This is an equation that just kind of estimates how much long-wave radiation is going out from the water depending on what the water temperature is. And so the Stefan-Boltzmann constant, that is related to predicting how many watts per square meter are going to be emitted based on the water temperature. And so that constant says that 5.67 times 10 to the minus 8 watts per meter squared per Kelvin to the fourth. So when we plug it into this equation, this radiation emitted is the first thing what we want to know. And so we have to convert the water temperature into Kelvin from Celsius. So the water temperature that was measured for this day was 26 Celsius. And so T sub P will be 26 plus 273.15. So the water temperature is 299.15 Kelvin. So we want to know the water temperature because it's going to tell us the outgoing long-wave radiation from the lagoon. So the radiation emitted R sub E is, okay, the formula E, Stefan-Boltzmann constant, T sub P to the fourth. Okay, so 0.995 times 5.67 times 10 to the negative 8th watts per meter squared Kelvin to the fourth, and then 299.15 Kelvin to the fourth. If you punch those numbers into your calculator, what you'll get is it's 451.8 watts per meter squared. So just based on its temperature, that's how much radiation is going out into space from the water. And remember, that's important to know because we have to do this energy balance to find out how much radiation is there to actually vaporize the water. Because it takes a certain amount of energy to take it from the liquid phase into the vapor phase. And so our ultimate goal here is to calculate R sub n. Now that we know how much is being emitted, we can estimate the net radiation available to drive evaporation. So net radiation available to drive evaporation. R sub n is R sub I, 1 minus alpha, minus R sub E. Okay, so it was measured with a radiometer, the incident radiation there, 978 watts per meter squared. So that's how much is coming in, 978 watts per meter squared. 1 minus 0.35 because some of it's reflected, so we want to subtract out the part that's reflected, and all that's left over is the 65% that isn't reflected. So there's the non-reflected incoming radiation minus the outgoing radiation, 451.8 watts per meter squared. So the net radiation that's left over is 183.9 watts per meter squared. So that's the energy that we can use to drive evaporation. So if we put that into the formula for E sub R, E sub R is going to be that net radiation of 183.9 watts per meter squared divided by L sub V. The L sub V here depends on the temperature, so we need to calculate that L sub V. Let's do that. L sub V is 2.501 times 10 to the 6th minus 2370 times the temperature. In our case, we put in the air temperature of 28.5 degrees Celsius. And that gives us a latent heat of vaporization of 2,433,455. The units there are joules per kilogram, which is the same as watt seconds per kilogram.
We don't need to convert that to Kelvin, or is that 2270 takes that into account?
The temperature here?
Yeah.
Yeah, it doesn't need to be converted to Kelvin. No. Okay, so we put the latent heat of vaporization, because we're substituting into this formula for E sub R, in the denominator. So it's 433, 455, and just so we can watch the units cancel out, I'm going to write it in terms of watt seconds per kilogram. And then the density of the water was 996.3 kilograms per cubic meter. at the temperature in question. We just go to a density table for water, and the water temperature was 26 degrees Celsius. Okay, so what that tells us, if we do the calculations there, it's 7.58 times 10 to the minus 8 meters per second. So length per time. And if we want to find out, like, in terms that maybe is a little bit more understandable, we could multiply that by the number of seconds per day. So there's 86,400 seconds per day. And then multiply that by 1,000 millimeters per meter. And what we'll get is the E sub r is 6.55 millimeters per day. That would be the evaporation rate, which assumes unlimited transport of the water vapor that is going from the liquid phase to the vapor phase. So all we're doing is we're saying there is a certain amount of radiation. I'll give you a moment to finish copying that down, and then we'll talk about how reasonable it might be. Mm-hmm. Yeah, so this is closer to the equator, and so they probably have more radiation than the global average. But think about, what have we just assumed here? Maybe it wasn't we, maybe it was me. Maybe I was the one who made the assumption. All right, this radiation was measured at noon, but we projected it through the entire day. When I multiplied by 86,400, that's essentially saying that you're going to have that same solar radiation through the entire 24-hour cycle. And so, of course, that's not accurate. So the more accurate way to do it would be to find some data source that says how much radiation is there at 6 a.m., at 7 a.m., at 8 a.m., and do this in 1-hour steps to find the radiation, average that during a 1-hour period, and then calculate, well, what is the evaporation rate during the 1-hour period, and then add up all of the, and then convert it from an evaporation rate to an evaporation depth by multiplying by the time of that increment, and then do it over time. Because what we'll see is that during a 24-hour cycle, if we start at midnight, 12 a.m., of course, there's not going to be any solar radiation. But then the sun increases and it decreases again. So maybe it's 6 a.m. to 6 p.m. that there's any appreciable solar radiation, and it peaks around noon. So what we'd need to do is divide that up into pieces and find out how much radiation there is during each of those pieces and predict the evaporation on an hourly basis and add it up. Yeah?
So for ER, would we want that in, say, millimeters per hour? Do that for each hour, add them all up?
Well, it's going to come out in terms of meters per second, just because this latent heat of vaporization has a second time constant. So yeah, so you'll get meters per second, and maybe it would make sense to multiply that by just the number of seconds per hour. So 3,600 seconds per hour, and then do it for each hour.
Average and get like the total daily if you do it 24-hour period.
Mm-hmm. I don't know, would it be the same if you average it as if you multiply the rate by the number of seconds and then divide by, maybe. Ultimately, what you want to know is how many millimeters of evaporation was there during the day. And so you find out how many millimeters of evaporation there is every hour, and then just add up the hours that there was evaporation, and that will tell you the number of millimeters during the day.
Because you may not have it all day.
Yeah.
Okay.
Yeah. If my memory serves, then you've got a problem where you're going to be doing this, where there's a, well, we've got some time. Let's look at the homework. It's been a year since I looked at it, but I think that there's a data source in New Mexico, like a good solar radiation data source in New Mexico. Yeah, the National Solar Radiation Database. And what you can do is you can get the solar radiation data for Albuquerque on an hourly basis. And so what I'm going to ask you to do is estimate the evaporation in Albuquerque using that actual solar data. So what you'll be doing is there's a combined method. This is just the energy method. What we'll talk about on Thursday is something called the aerodynamic method, which takes wind into account. And then the combined method is kind of a blend of the two. The combined method says we need to balance our energy balance and the transport term that takes wind into account and come up with kind of like an equation that accounts for both of those factors and blends it together. So that's what we'll do on Thursday. If you want to get a start on the homework, you could obtain the data and start formatting it. I give you some formatting instructions here on the way that you need to set it up, but we won't actually have the full-fledged combined equation until Thursday's class is finished. All right, that's all I got for you today. I'll see you next week.